afternoon. Today, as promised, I want to look at how you code up this Hermite polynomial interpolation. I'll also take advantage of the opportunity to introduce another refinement. Some days I work on my Windows computer, other days I run Linux, either in actuality or in a virtual machine, and the issue about forward slashes and backslashes in describing where files are located at becomes very annoying after a while. So today I'm going to work on a Linux machine, and I'm going to tell you an easy way to go back and forth if you don't know about it already. This gives me an excuse to at least mention the character data type. So for now, I'm in the directory or folder, if you like to say that, /home /Dr. G /Hermite /input output. This is the directory in which I'm going to read my data from and put my output into. So far our output is the report.txt file and also the files that let us plot the polynomial that we've calculated. So the first thing I'm going to look at is to make sure that my input-output file is correct. I've called it data.txt. N is 2, meaning I have 3 data points. The x-coordinates are 0, 1, and 2. The function values are all 0, and the slopes are pi or negative pi to about 15 significant figures. It will be an interesting thing to observe when I read out of this file and print it to file number 7, report.txt, whether it gets all those digits right or not. Next, I want to look at the code. Now I'm in the directory home, drg, hermite code. I've written my program. I've called it hermite.f90. It's got 2 new features to it. One, the actual Hermite calculation, and the other, I'm going to do something tricky with how I tell it where the input and output go. So here we are up at the top. Very little has changed so far, except I have a new line. Character, and in parentheses, len equals 50, comma, parameter, meaning this isn't a variable, you can't change its value. The name of the Fortran variable is going to be called path, and it's going to be as a character string contained within the quote marks, /home /drg /hermite quote mark. It's very important not to put any spaces in that because that will confuse everything. Also, the len equals 50 says set aside 50 character-sized storage units for this variable, path. You'll notice the path isn't really 50 units long, so what Fortran will do is it will pad the rest of it out with blank spaces. The way you get rid of those blank spaces is don't deal directly with variable path, use the trim command. Trim takes away all the trailing blank that's in this character string here. The other thing that you need to know is that 2 forward slashes in Fortran mean I've got 2 character strings. I want to take the first one, keep it where it is, and I want to concatenate the second one to the right of it. That is to say, I just want to slap the 2 strings together. So here, when I open file number 9, trim path is just /home/drg/hermite/ with all of the blank spaces taken out. // means slap the character string forward quote mark input output forward quote mark data.txt onto the end of the trimmed path. If I do it this way, when I go back and forth between my computers, life is relatively easy. If I'm doing Linux or some other Unix type operating system, I'll use something like this, what I'm actually doing. If I was using Windows, I would put an exclamation point in front of that C to turn this into a comment. I would take this exclamation point out, and now when the program is run, the path is going to be C \users \Dr. G \Hermite, and I don't have to change a whole bunch of these open statements. I only have to change that one line. So, as usual, except for this refinement. Hello? That was Ashley from Visa Master Account blah hung up on her. Anyway, aside from the way that I'm describing the input-output location, so far pretty much the same. As before, there is, though, setting up the Z array, setting up the FZ array, which I have to do if I'm going to do Hermite. I'm going to have a subroutine called compute Hermite. All it's going to do is it's going to calculate the coefficients of the Hermite polynomial. Now, there were design decisions about what to send compute Hermite exactly. I decided that it would be best to send it N and M. Hermite needs to know about the derivatives at x0 through xn. I've got to send it the z values and the f of z values, and I have to send it an array to put the coefficients of the Hermite polynomial in. Hermite does not need to know about the array xv or the array fv. That relevant information has been put in the appropriate places in zv and f of zv. Now, we have previously done a sanity check by taking each of the x values out of our data set, evaluating the Newton polynomial, and seeing if it gives me the right answer or not. We print out the difference between the known function value and the value of the polynomial. It might not be clear, but I don't need to write a new evaluation routine. If you think about what the variables that I've highlighted are, p is going to be the value of a polynomial written in a certain form. That first variable, the n, is the largest index in my data set. The next variable is the set of independent variable values in my data set. A is the coefficients of the polynomial that I've found, and the x just represents the number at which I want to evaluate the polynomial in question. If you think about it, nothing needs to be changed here. M in the Hermite polynomial is the biggest index in the problem. The independent variables are in ZV. I've stored the coefficients of the Hermite polynomial into array B, and x is the number that I want to evaluate the polynomial at. A purist might say I should be using the letter Z there and here, That's just silliness, though. It's a number that I'm going to stick into my polynomial. Since it's one of my x values out of my data set, it's probably best to just keep calling it x. Then we're going to create data plot, polyplot, now Hermite plot. I'm doing the names of the file complete with location as I did the other ones. This chunk of code is what we did to prepare a graph of 101 points on the graph of the Newton interpolating polynomial, which, as you'll remember, was not a very interesting polynomial. The graph is a horizontal straight line. If you compare what I've got highlighted to this, you will see it is exactly the same thing, except I'm not evaluating the Newton polynomial, I'm evaluating the Hermite polynomial instead, hence the use of m, zv, b, and x. Deallocate your memory, and that is the end of the program. In the rest of the work, the only thing that is any different from what we've done before when we were doing the Newton form of the polynomial is that we have this new subroutine called compute Hermite. So that's the only other thing we have to look at that's new. So here we are down in compute Hermite. We do all the usual declarations and dimensioning things. What do? Column number 0 of my table are the function values. That's done there. Then I print it out to file number 7 so that I can check it and make sure it is what it's supposed to be. Now, column number 1 of the table, k equals 1, second index in the table equal 1, that has to be done specially. When the index is odd, I'm supposed to use a derivative value, and when the index is even, I'm supposed to just use the ordinary recursion formula. There's various ways that you can describe this, but we figured out that the derivative values went into slots 1, 3, 5, 7 down to m. So it seemed to me like it would be easiest to index this with the index on the x data. So the x data has indexes that go from 0 to n. I'm going to look at f prime at x0, f prime at x1 through f prime at xn. The consecutive odd numbers that correspond to 0, 1, 2, 3 to n are 2 times that index I plus 1. If you'll refer back to the hand calculation that we did in the previous videos, you'll see that this puts the derivative information in the correct places. Of course, you also have to deal with the even indexes. We described both in a class meeting and in the hand calculation how to do this. So I'll just remind you that for each index 1 to n, I'm going to store something into index number 2 times I in column 1. And the way I do this is with the usual divided difference formula. So that part of column k equal 1 is done the usual way. Then I print it out to make sure everything is good. Column k equals 0 has the data. Column k equal 1 had to be treated specially. But columns k equals 2 through m are done using the usual recursion formula. So we'll have a loop, do k equal 2 to n. Within each column k equal 2 out to m, row index will be the column index out to the biggest index in the table. So we will do I equals k to m. And how did we get tki? We take the number in the table that's immediately to the left of the ik position. That would be ik minus 1. We take the number that's in that position and subtract away the number that's directly above it in the table. Then we divide by independent variable index I minus independent variable index I minus k. When we wrote our initial code for the Newton method, we decided that that's how the indexing should go. Then I print column k out so that I can make sure that it's doing as it should. And then we're basically done. I store the diagonal entries of the t table into the one-dimensional array B. These are going to be the coefficients of the Hermite polynomial. So after that, we go back to the main program. It calculates the sanity checks, it creates the graphs that we can then look at, and we're done. So let me compile this. I'd like to tell you that I sat down in front of the computer and put all of these changes and additions in. I typed it all in one sitting, then I ran it, and it worked perfectly the first time. I'd like to tell you that, but I would be lying, because that's firstly not how I did it, and secondly, it didn't go that smoothly either. Firstly, type stuff in a little bit at a time and make sure, firstly, things compile, and secondly, if something's actually being calculated, make sure that it's right. And then after that, we have basic errors like syntax errors and spelling errors and typing errors. I had forgotten that to concatenate two strings, it's slash slash. I had it in my mind somehow that it was ampersand ampersand. When I tried to compile that, the compiler didn't like it. So naturally, I had to go look up how to concatenate strings again. This is to be expected. However, after some messing around, my program compiles without complaint. I run it. It tells me it's creating data plot, polyplot, and Hermite plot. I should have put in a print statement that told me where it's printing them into also, but that's all right. So I've changed directory now. So data plot, Hermite plot, report plot were created at about 1332, and I've just checked the time and date. It's now 1333. So these files were created just a moment ago. The data.txt file has been sitting on this computer for a few days, though. It was made on October 12th at about 2 o'clock. About 2 o'clock? It was 2 o'clock in the morning. No comment. Anyway, I want to look at the graphs of these things. So now I want to run my program. So I'll make sure I've compiled it and got the latest version. I'll run my program. The time and date is it's 36 minutes after 1 on Friday. The reason I wanted to say that is to make sure these files are what I think they are and not left over from some previous work. So I'm going to change over into the folder that has my input and output in it. Data plot, Hermite plot, polyplot, and report.txt were created at 36 minutes after 1 on Friday. If you look at the time and date, it was 36 minutes after 1 on a Friday. So these files were just created a moment ago. Thing number 1, let's look at the report. So I printed out the path to the code and the data folders, and that is the correct path. I read the data in, printed it out. The X numbers are 0, 1, and 2. The function values are all 0, and the derivative values are to a high number of decimal places, pi, negative pi, and pi. It has correctly read the data. Now I go off and I do the divided difference using only the function values, and what I get for answers are all zeros, as they should be. This is what happened in the hand calculation. I'm storing x values twice and function values twice to get the z array and the fzv array. After I do that, I go in and I calculate one column at a time the columns of the table for the Hermite method. So column number 0 consists entirely of zeros, which is what we said it was going to. Column number 1 is pi, 0, negative pi, 0, pi. If you'll look back to the handwork that we did, that's correct. Column number 2 of the Hermite table is negative pi, pi, and pi. That's what it's supposed to be. Column 3, 0, pi, 0, which is what it's supposed to be. Column 4 is pi over 2 and negative pi over 2. And the number in the last column is negative of pi over 2. These are the numbers we got by doing the hand calculation. The divided differences are T00, T11, T22, T33, T44, and T55. We do our sanity check. Now we're only looking at function values here, but the sanity check is correct for the X's and correct for the Hermite table as well. So this tells me I have really good confidence that I am calculating the Hermite polynomial correctly. I want to do more than just that though. So I'm going to run GNU plot. If you plot data plot, this is the data except we've taken the line where I told it what the n was out. That would confuse GNU plot. If I graph this, there's x equal 1, y equals 0. It's a little hard to see, but there is x equals 0, y equals 0, and there is, you can see just beyond the border of the graph, you can see right here, you can see right there, here, there is no extension to the right of that vertical line, and here there is. That's where my other data point is. Over on the left side, there is no extension to the left of the vertical line. This is part of the symbol for one of my data points. So my data points all lie on a horizontal straight line just as they're supposed to. There is no use in drawing in the graph of the Newton polynomial. We know what it's going to look like. It's a horizontal straight line with all y coordinates 0. So instead of doing that, I'm going to draw the Hermite polynomial. Now, if I just do it here, it's going to plot the data points with big pluses, and it's going to be a little bit harder to see what's going on. So I'm going to tell it to plot the things as tiny little dots and connect the dots with straight line segments. And as you can see, this is totally different from a horizontal straight line. So it looks as though this may be a considerable improvement over the original Newton version. I haven't explicitly said so, but what we've been talking about are 3 points on the graph of y equals sine of pi times x. GNU plot doesn't have constants much installed, so I'm just going to be lazy. So I've made pi as an abbreviation for the arc cosine of -1, comma. I want to plot what I think the actual function is, sine of pi times x. Now, the graph of the Hermite polynomial is the graph of a polynomial. The sine function is not a polynomial. That means these two things are not going to be exactly the same thing, but optimistically, they'll be a lot more close together than just using a horizontal straight line. And as you can see, the approximation is quite good. Near the maximum and minimum, there are discernible differences, but even so, all the way across the interval from x equals 0 to x equals 2, the Hermite polynomial is a pretty good approximation to the actual graph of the sine function. So we started off with the theory. This is where we took the table and let the epsilons go to 0. We have worked out in detail a hand calculation. We've written a program to do that calculation, including the new thing about the character strings. And looking at our output, it looks as though everything is fine. This works correctly. Coming up soon, I'll have a discussion of what was talked about in class on Wednesday, which were an elementary integration method and also an error analysis of it. Then after that, we will look at some more sophisticated integration methods, and after we get done talking with that, it'll be on to differential equations. I hope everyone's having a good week. Have a good weekend. I'll talk to you again real soon.